Work is purely a force creating a displacement. So work being equal to a force multiplied by some displacement. Work is a measure of energy. So joules is our measure of energy. Work is force times displacement. And we use energy as the ability to do work. More on that to come in a little bit when we go into energy. If I have a flat surface like this, and I put an object on that said flat surface, if I apply a force straight into the surface, what is the work done to this object? So no displacement caused, therefore no work. If I apply a force in that direction and our object moves there to there, so my object has moved from this point here over to there, has work been completed? As there is displacement, work has been done. What happens though if I apply a force like that to the object? So the object, it's not being pushed directly into the surface, but it's not being pushed directly parallel to the surface. And the object still moves by the same amount as if it was being pushed by our red arrow. Is work being done on the system? So work is still being done. Am I applying more energy to this situation? Am I doing more than what I'm actually needing to? Yes. The main thing is that we are only applying it to the parallel component, so it would be that component there of my force. Work is being done, but only in the component that has displacement. Generally, when you come across this formula, it is going to have a cosine theta attached to it. So work is going to be equal to our force times the displacement times by the cosine of theta. I prefer not to chuck that in, mainly because I expect you to know that if a component of the force is not causing a displacement, no work is being done. All right, the next one that we're going to be looking at, surprisingly, is we looked at work. Now we need to look at energy. Energy is the ability to do work. So work is measured in joules, which is our measurement of energy. But energy is the ability, in a sense, to see how an object is moving, where energy is stored, and how we can utilize that energy into different situations. So there's two major types of energy that we're going to be looking at, potential and kinetic. I'm going to go with potential, mainly because it's the easiest one to describe first. Potential energy, I'm happy if we go PE. So for potential energy, you could do it as E with a subscripted P for energy potential, or you can do it as U. In this situation, it's going to be G. UG is going to be our gravitational potential energy, and that's what we're dealing with in terms of potential energy here. It is being created by gravity. Energy, it has the ability to do work, so our potential energy is going to be equal to our work. Work is equal to our force times by some displacement. If we're talking about a gravitational potential energy, the acceleration is going to be G. Our acceleration in this situation is the acceleration due to gravity. So we're going to have this equal to mg. But in this situation, S is the displacement. So if we think about a gravitational potential energy, we worry about how high it is off a surface. So we refer to, instead of S being the displacement it moves, we talk about H being the height of the object. I've got a set of stairs here that go up and that go down the other side. I move a ball up the stairs to the very top. I also move the same ball from the bottom directly up. Which one has more potential energy? They have the same potential energy. That is because they have the same vertical displacement. The same ball has the same mass. Gravity has not changed because it has not gone to a different planet. It purely has the same gravitational potential energy because they are at the same height. Energy is not going to be created or destroyed. It is only going to be transferred. And this is our conservation of energy. I am only going to use kinetic energy, and I use the energy stored chemically inside of me to climb on top of the bench. I then have a store of gravitational potential energy, and then I jump down, converting that gravitational potential energy into kinetic energy, and then finally into thermal and sound, which you could hear as I landed with a thump. Kinetic energy. It's the energy of something that is moving. It is going to be half mv squared. Our derivation for this comes actually from an equation of motion. That one is our v squared is equal to u squared plus 2as. If we use this formula, we can rearrange for some acceleration and displacement. We use this because acceleration and displacement can be rearranged to become force and displacement. Because force is equal to mass times acceleration. So that means our acceleration is going to be equal to our force divided by our mass. Rearranging our equation, we get that 2as is then going to be equal to v squared minus u squared. Our F on m times by our displacement is then going to be equal to a half outside of our v squared minus u squared. And then we can expand it out, so we're going to get our force times displacement, which is our work, which is our kinetic energy, is going to be equal to a half m, but now we can expand those brackets. So we would get v squared minus a half m u squared. So when we do work on an object, we actually see a change in its kinetic energy. An object can be moving at a constant velocity, and it will have kinetic energy, but it is not doing any work. Energy has the potential to do work. So by moving at a constant velocity, there is no change in its velocity, so therefore it is not doing any work, but it does have the ability to do it if it was going to start changing its velocity. So this is what I mean by the fact that energy has the potential to do work, but we need something to change with our energy to actually get it to achieve work. If you square velocity, velocity is a vector, but if you square a negative, you get a positive, and if you square a positive, you also get a positive. So therefore, energy is actually scalar. Does not require a direction. You need to think about where the energy is going to be stored. So for example, lifting up the pencil case, I am doing work by lifting it up. By me doing work, I am storing it as energy. It now has gravitational potential energy. I drop it, it converts from gravitational down as we go to being kinetic before it reaches the bottom where it becomes thermal energy and sound. Energy is transferred and work is done along the way. Are we happy to power on and move on to the next component? Fantastic, in which case let's power on to power. So far we've dealt with the idea that work is a force times the displacement. One thing not involved in this is time. So power is involving that. If I was to make an event happen quicker, would you expect there to be more power usage or less power usage? More. Mainly because I could lift up this trolley. I could do it really slowly. I'm not really putting in much effort into it. It's taking a long time to do though. So therefore, my power usage in this regard is very low. I could do the same thing and just lift it up really fast, and my power usage would be a lot more. Mainly because even though I've done, in a sense, the same energy by moving an object from a lower height to a higher height, the time that it takes me to do that means whether I need to put in more or less energy. So power is a measure of energy used per second. Power with a capital P is equal to our work divided by our time. Can anybody guess what the unit of power is? What could it be? I know, come on, can't you get me a bad joke when I want it? Yes, power is measured in watts. It's not W-H-A-T though, it's W-A-T-T-S. So our watts with a symbol of W So that is going to be our joules per second. Where have you heard of watts before? Electricity, right? So whenever you buy an appliance or anything like that, you can actually get an energy rating on it, so the amount of energy that's going to be used. Generally, they would say that an appliance is 2,000 kilowatts. So that means that it's going to be using, 2,000 kilowatts would be 2,000 times 1,000 joules per second is how much energy it would use, which is a lot of energy. That would be 2 megajoules per second, right? The other way that you would hear it is through the electricity company, and if you've ever looked at a power bill, your power bill will read it as kilowatt hours. What is that? Your electricity company wants to bill you on how much electricity you use. So if you look at the units of this, well, kilo is just times by 1,000. Our watts is joules per second, right? Hours is just, well, you've got 60 minutes in an hour times by 60 seconds in an hour. So this means you get 3,600 seconds. So when you get billed in kilowatt hours, you are actually getting billed energy. That is the amount of energy that you have used in a day, in a month, in a quarter, depending on how your electricity company sends that information through to you. However, to make the best efficiency of this lesson, we need to cover one last thing. And that surprisingly is efficiency. We are generally not 100% efficient in terms of the fact that I've spent the last 30 minutes talking to you, and how much have you retained in that 30 minutes? Hopefully all 30 minutes of it. But I am outputting some power, some information to you. The amount of power input, or the amount of power that you have received, the amount of information that you have received, is probably not all of it. So the efficiency of this lesson, though we did cover a lot of content, may not be great. So our efficiency is a measure of the power that we put into the system versus the power that we get out of the system. What is the unit of efficiency? It is unitless, right? Because you have power out divided by power in, you have watts divided by watts. Watts divided by watts is the same as x divided by x, which is equal to 1. So therefore, efficiency is unitless. It is a measure of how much you are getting out of a situation. So you could, in a sense, look at this in terms of the energy provided into the system versus how much energy you're getting out of the system, or some other component, mainly because it is primarily about power, but realistically, if the rest is constant, it's energy divided by energy. I know we've been very efficient, but hopefully we're not going to collide and come up with any problems at the moment. So there's one last thing I need to come up and talk about. One last thing before we collide into some problems. We're going to talk about collisions. We had the idea of conservation of energy, right? So conservation of energy says that the energy initially is going to be equal to our energy finally, which generally we take as being our potential energy, so mgh, plus our kinetic energy, half mv squared, is going to be equal to its final one. So I'm going to add a 1 there and a 1 there. mgh2 plus a half mv2 squared. So our initial energy is going to be equal to our final energy. However, something to be aware in this situation is, where's my thermal energy? Where is my sound? It's not there either. So I have no thermal energy and I have no sound being created as part of this relationship. We have three main collisions. We have an elastic collision, we have an inelastic collision, and finally we have a partially elastic collision. Or is it primarily just a real collision? So in an elastic collision, Our energy is conserved. Our momentum is conserved. And objects will bounce off each other. The best option we have for an elastic collision is air molecules and behaviors in terms of atoms and their movements. So when an atom is flying around, and let's say, or a molecule is flying around in our air, it can bounce and collide with things, and that is our best approximation for an elastic collision. Energy is going to be conserved, momentum is going to be conserved. As they collide together, they're going to perfectly bounce off each other because no energy is going to be lost to sound or thermal energy. The other way to come across an elastic collision would be with a physics problem. So the fact is, inside of our physics problems, you will have elastic collisions, mainly because we're going to not take into account a lot of that thermal energy loss. We won't have any friction being applied to the situation on a frictionless track and things, so you can have conservation of energy in terms of a physics problem. In an inelastic collision, we have objects stick together. In all collisions, what is conserved? Momentum. Yes, so momentum is conserved in inelastic collisions. However, energy is not always conserved. Finally, we have our partially elastic. Surprisingly, it's going to be similar to our elastic collision, so that objects will bounce off each other. Momentum is conserved. Energy does not have to be conserved.